Hello and welcome back to Whaling to Watching on Oceans Live. I'm your host, Kate Thompson, with NOAA's Office of National Marine Sanctuaries, coming to you live from the tip of Cape Cod in Provincetown, Massachusetts, for the 38th voyage of the Charles W. Morgan. The Morgan is the last surviving wooden whale ship in the world, and we're here at the Pilgrim Monument and Provincetown Museum, bringing you exclusive footage and interviews from this incredible ship's journey to the Stelwagen Bank National Marine Sanctuary. Brought to you by the Mystic Port Sea, home of the nation's leading maritime museum, the Morgan's 38th voyage continues through the weekend, and so does our coverage. Be sure to tune in at 10 a.m., noon, and 2 p.m. Eastern tomorrow and Sunday for the rest of the action. A big thanks to those who are watching our broadcast at our remote viewing sites, including the Mariners Museum in Newport News, Virginia, Mystic Seaport in Mystic, Connecticut, Thunder Bay National Marine Sanctuary in Alpena, Michigan, and the Moku Papapa Discovery Center in Hilo, Hawaii. We've had some terrific guests on our shows today, and we've got another great lineup for this episode to help us explore how technology has evolved from the primitive tools of early whalers to the cutting-edge gear used by modern whale scientists. Here with me in studio, I'm pleased to welcome Dr. Dwight Coleman, Director of the University of Rhode Island's Inner Space Center. Thanks, Dwight, for being here.
My pleasure.
And also joining us is Ivar Babb, Director of NURTEC with Connecticut's Northeast Underwater Research, Technology, and Education Center.
Happy to be here with you today.
Thanks, Ivar. And it's a full house right now out on the Charles W. Morgan, where our correspondent, Matthew Lawrence, is going to be chatting with several special guests. Matt, are things starting to get a little crowded on deck there?
Great, we're having a great time out here on the deck of the Charles W. Morgan. All of the various activities are well underway. The sails are drawing well, and we are just skimming through the water. It is a gorgeous day in the Stelwagen National Marine Sanctuary.
Great, Matt. Well, joining Matt on the deck, I see right there, is we have Dr. David Wiley, who's the research coordinator for the Stelwagen Bank National Marine Sanctuary. We also have with us out there 3 of the 38th Voyagers, Mystic Seaport's rotating group of professionals from diverse backgrounds who are documenting their experiences on each leg of the voyage. There's Lisa Gilbert, an associate professor of Geosciences and Marine Sciences at Williams College, Frank Reed, an expert on celestial navigation, and Michael Witney, an associate professor of Marine Sciences at the University of Connecticut. And last, but certainly not least, we have National Geographic Explorer in Residence and returning Oceans Live guest, Sylvia Earle. Matt, can you have Dave tell us about some specific whale behavior research that's happening out there in the sanctuary?
Absolutely, Kate, here. Well, standing next to me is David Wiley here, and we're going to talk a little bit about his research here in the Stelwagen Bank Sanctuary. Dave, you know, you study whales for many years here in the Stelwagen Bank Sanctuary, and whenever I see video of your research, I think you must be the man who knows what the whalers felt like. You get closer to the whales than just about anyone else. Tell me what through your mind when you're out there tagging whales.
Well, yeah, actually, while we were watching them in the longboats trying to go towards the animals, it was interesting to kind of compare our experiences with what they're doing and what they did, 100, 200 years ago. And, the first thing you have to worry about, of course, is being safe, because they are big animals, and although they're not aggressive particularly, they certainly have the ability to knock over a boat or come down on top of a boat. And so it's a little bit of a concern whenever you're that close to an animal that's large. And, of course, it's a totally wild animal doing whatever it wants. So it's a bit of an issue.
Obviously, many things going through your mind, as well as trying to conduct the scientific research that's so important for the species conservation. Could you tell us a little bit more about just the whole process that you do to tag the whales and really what that research is revealing to you?
Sure, we use a very similar process to what we used to do to harpoon whales, except that we use suction cups. So we use a long pole. We carefully come upon them with a inflatable boat, come as close to them as we can, because the pole is only about 25 feet long, without injuring the animal. So our first priority is to keep the people safe. Our second priority is to keep the animals safe. And our third priority is actually to do the research. So the tags are fixed to the animal by a suction cup. The tag is stuck on the tip of the pole, so again we maneuver the boat up next to the animals as they're moving and pop it on their back, and then it'll stay on depending on actually how we program it, usually between 10 and 20 hours.
That doesn't give you that much time. I've heard that there are satellite tags that last much longer, so what are these tags revealing to you?
Yeah, the tags that we use are very different than satellite tags. Satellite tags are really designed to give a few pieces of information once or twice a day for many, many months at a time. Our tags are collecting thousands and thousands of pieces of information every second, and are designed to give you a very fine-scale look at what's happening over a very short period of time. So we're really studying fine-scale foraging behavior as opposed to what a satellite tag gives you, which is long-term movement data.
So all of this data you're collecting, so how do you even look at that much data? How do you analyze it?
Yeah, that's definitely a trick. It's actually, one aspect of things is collecting data, but then making sense of those data is really the next key step. And we've been lucky enough to work with the University of New Hampshire, this person named Colin Ware, who's just a data visualization guru and expert. He writes textbooks on data visualization, and he adopted our project as one of his pet projects. So he's actually developed entire computer visualization programs that is designed to visualize and analyze our tag data. It's a program called TrackPlot and another one called GeoZooey 4D. And they basically let us create almost a virtual whale that swims to the tag data. So we can look at what an animal did at any one point in time, and then look at what it did before that point in time and after that point in time by looking at these different programs. So they've really been able to revolutionize how we not only get tag data, but then use tag data.
So could you share a little bit about some of the discoveries you might have made? We heard earlier from Jim Hain talking about various whale feeding behavior. I understand that those tags are actually revealing a lot of information about that.
Yeah, Jim did a lot of the pioneering work using surface observations to try to figure out what animals we were doing subsurface. The nice thing about these tags is that they tell us then what the animals are doing under the water, which has always been one of the huge mysteries. And a lot of us confirmed some of the things that Jim found. By looking at jaw scuffing, he was determining that the animals were probably feeding along the bottom. And using our tag data, we're finding that absolutely they feed right along the bottom, but not only that they feed in groups. So they actually cooperate to feed along the bottom and come head-to-head along the bottom and evidently push the sand lance towards each other as they're trying to capture them, because sand lance are really hard to catch. I'm amazed that whales can do it. They're really fast. We have a hard time catching them in nets, but these animals catch thousands of pounds of them every day just with their mouths. And it seems that they do it by working cooperatively together, either on the surface using bubble nets or on the bottom using this kind of crazy side-turning behavior and going head-to-head, which we haven't totally figured out, but using the combination of DTAG data, which is the computerized data, and CritterCam data, which actually we put a camera on the back of the whale to see what the whale is seeing, have been able to give us a lot of information about what they're doing, but we still have a lot to learn.
Many, many mysteries still in the ocean to be uncovered.
Yeah, that's for sure.
Well, Kate, thanks so much. We've had a great interview here with David Wiley, and back to you in the studio.
Great, Matt. So back here in the studio, we're just wondering a little bit about those 38 Voyagers and the people that you have lined up to tell us a little bit more about the different types of navigation that the whale ship used to use and what it uses today. So starting with Lisa Gilbert, can you tell us a little bit about the history of how whalers navigated the sea?
Fantastic. Now standing next to me is Lisa Gilbert, and we're very pleased to have you here on Oceans Live. I'm wondering if you can tell us a little bit about the technology whalers might have used to sample the seafloor and learn about where they were.
That's great. Thanks. I'm pleased to be here. It's been a great day out on the Morgan. Yeah, so some of the technology that whalers would have used in the 19th century to figure out where they were would be things, of course, like charts we use today and sighting points of land, just as we do today. But certainly the charts were less complete in the 19th century. And the tools were much less advanced. I have a 19th century tool here. I can grab it. It's right over here.
Yeah, Lisa, why don't you step over and grab that for us to give viewers a chance to see one of these items. Oh, that's quite an antique-looking piece of equipment. What is it?
Yeah, so this is a lead line used for sounding the depth of the ocean. And so when you get near to shore, of course, you don't want to run aground.
No.
Nobody wants to do that. So, so these lines were used, tied off somewhere safely, just as we do with technology today, to the ship, and then the lead was tossed overboard, and you can see the markings here to figure out sort of pretty quickly how deep the water is. And then inside the cup would be some tallow, something sticky, fat, that would allow for some sample of the bottom to be brought back to the surface. And so then you'd know if you were over mud or sand or gravel, which might be useful for a couple of reasons. One would be safety, of course. Knowing how deep it is and what's there. If you're going to anchor, you want to pick a good substrate for anchoring in. And then also, if you know what's on the bottom, you might have some idea also about what might be living in the benthic ecosystem and therefore sort of the whole food web too. So even if you're looking for whales, it might be useful to know what the sediment is on the bottom.
Oh, that's very fantastic. But nowadays, we do it a little differently. Can you tell us about the technology nowadays that we use to essentially chart the bottom?
Right. Absolutely. Using the lead line today would take a lot of time to chart the seafloor if you were dropping that line over, pulling it back up, dropping it. And so today what we use is much more advanced. Multi-beam sonar is in common use now, where a lot of different, a large swath of sound is sent out in many directions from the ship, as a ship could be traveling along at a pretty good rate, almost continuously collecting information about how deep the bottom is, not at one point, but maybe hundreds of points below the bottom. So depending on how deep the water is, for miles across, getting a swath of the bathymetry. And even from that too, we use backscatter imagery to figure out what is on the bottom as well. You can tell the difference between sand and mud and gravel using the acoustics as well. So it's sort of a modern version of the lead line done in many places at once very quickly.
So that backscatter data is something like looking at the little sample of sediment that came up in the tallow end of the lead line, but over much larger areas. Is that right?
That's right, and with a little bit of interpretation of complex data, yeah.
Well, are you familiar with Henry Stelwagen? He was a hydrographer that actually mapped Stelwagen Bank National Marine Sanctuary's seafloor.
Yeah, I've read a little bit about him mapping here in the 1854. Is that right? Yeah, go ahead.
Yeah, that's absolutely right. 1854 is when he made the first scientific map of the sanctuary, I believe.
That's right, and he had a pretty interesting version of the lead line where you could get more than just like a little stickiness on the edge of a lead line, where you could actually get a little cup sample. Our first kind of bottom grab of sample on the edge of his Stelwagen cup.
And I guess it was very important to know about the composition of Stelwagen Bank, because that would allow mariners to sort of know when they were crossing in and getting near to Boston if it was maybe foggy. Is that right?
Absolutely. You can't always use points of land to figure out where you're going. The weather certainly changes a lot in New England. So being able to use the bottom, even though you can't see it either, can be really crucial information for safety and navigation.
Thank you so much, Lisa. That was fantastic. Thank you for sharing. Enjoy the rest of the voyage. Kate?
So yeah,
bring on
hey
some
Matt,
more
so on the subject
Voyagers.
of navigation, I believe we have somebody else out there, Frank Reed, who's an expert on celestial navigation.
Up on over here, and we'll have a little bit of a primer on how mariners use the stars to be able to get from point A to point B. Hi there, Frank. How are you? Nice to have you on the show. Why don't you tell folks a little bit about what you have in your hand here?
Okay, sure. This is an instrument for measuring the altitude of the sun and the stars above the horizon. And they use this to sail across the oceans to get from, here in New England out to the Pacific to hunt whales. This one's an octant. Others are called sextants. And they all work with mirrors to let you look in two different directions at once and measure the angle, exact angle in degrees and minutes of an angle.
Well, it certainly doesn't look quite like the GPSs that we all have in our cars nowadays, but was this a pretty accurate way to navigate?
Sure, within a mile or so, and you can see that far, so that's good enough, right? And I used it today at high noon to get our latitude within about a mile, so they can still do the same thing just today. In fact, I used an almanac from 1844 to get the data on the sun's position, so you can even use out-of-date data and it'll still work pretty well.
Well, I would imagine, does that take a certain amount of math to do, or is it all just looking up tables?
There's some math, but it's a kind of math that navigators learned how to do the same way you might do a cooking recipe, or say working out your taxes. It tells you to put one number in from column A and spot B, and you just work through it with addition and subtraction. So even though it was spherical trigonometry and logarithms, average people learned how to do it using little more than addition and subtraction.
So if the sun's not shining, or at night, can you also fix your position?
Yes, if the sun's not shining, if it's cloudy, the answer is simple. You wait. Or you keep track of your course and speed, and that's called dead reckoning. The dead part of it probably originating from the concept of dead water, because you don't really know if there are currents that are moving you around. So you keep track of course and speed and then add that up. And with any luck, it'll give you your approximate position. After maybe a few days, it'll be okay. But after a while, you have to get the stars back. So you keep hoping for the sun to come back out. And at night, they used the stars, but mostly navigation in the 19th century was a daytime activity. The sun was the single thing that they used. They used the sun at noon for latitude, and they used the sun in the early morning or in the late afternoon to get local time, basically turning this instrument into an accurate sundial. And then comparing the local time, the sundial time, against the time on a chronometer, which is just a really accurate clock showing Greenwich time, the difference in time between the two places, say if it's 4 p.m. in Greenwich and we find that it's 1 p.m. here, that difference in time, the hours multiplied by 15 degrees, gives you your longitude.
So it was also important to have a very accurate clock on board when those became available.
That's right. And it's interesting to note that on the very first voyage of the Charles W. Morgan in the 1840s, they only had one of these very accurate clocks, and they weren't entirely sure that it was working correctly. How could you know? It's a black box. It's the original black box, just a machine. You have no way of knowing whether it works correctly. So they had one other trick that they used, which is they measured the angle between the sun and the moon, and this was called a lunar. And because the moon is moving all the time, every night it's moved over 13 degrees or so, or it moves its own diameter in about 1 hour, we can use the moon as a sort of a natural chronometer in the sky. As it moves past various stars at night, or as the angle from the sun increases, it works just like a natural chronometer.
Thank you so much, Frank. That was very, very interesting, and I look forward to learning more about this myself. Kate, now we've learned about how whalers navigated the Earth and got from point A to point B.
Yeah, so I think you have one more person on there, out on board the Morgan with you, Mike Witney, who's an associate professor of marine sciences at the University of Connecticut.
Right, we needed to track down Mike Witney. He got waylaid by his drifter launches here, so
that's okay.
It's a little tough.
We can go to our wonderful guests here in the studio who can tell you a lot about drifters as well, and maybe we'll actually get to see his drifter later on. Okay?
I would appreciate that. We'll track him down, and hopefully he hasn't drifted away.
Thanks, Matt, and thanks, of course, to the 38 Voyagers for taking the time out of their busy schedules to talk to us on their wonderful trip out there on the beautiful day on the Morgan. But now in studio with me, I'm going to talk a little bit more about the advancement of technology for research in the ocean. And again, I have Dr. Dwight Coleman from the Inner Space Center at the University of Rhode Island, who's a wonderful partner with us on Oceans Live.
That's right.
And then, of course, we have Ivar Babb from NURTEC and the University of Connecticut. And both of you have done amazing trips around the world to do all kinds of research. But Dwight, you kind of are a sort of modern day whaler yourself. You pretty much researched everything out there, from deep sea vents to deep sea shipwrecks in the Black Sea to up in Lake Huron and some sinkholes up in Lake Huron and shipwrecks in Lake Huron as well. But can you tell us about some of the high-tech tools you use to explore the depths of the ocean?
Sure. Well, actually, there's a lot of similarities to the technology that they were describing with, the modern day tools that we use, of course, GPS to navigate around, and technology to map very accurately the depths, because as we explore the oceans, and one of the tools that we use to explore the the oceans is ROV technology, remotely operated vehicles. And before we dive an ROV anywhere, we need to have a good map of the seafloor, and what comes along with that is a good visualization of the seafloor as well. So the same tools that were described earlier about visualizing data and basically making sense of the environment that you're working in, we use to explore as well. So you need to navigate the ROVs very carefully. You need to dive on areas of the seafloor where you know the depths with high accuracy, and then use the GPS to navigate and determine the positions. And so when you collect samples, not with the lead line, but with the manipulator of the ROV, you're collecting a sample sort of in the same way, but you're able to do it much more accurately with the
I think we've got a shot here of Argus. You'd mentioned Argus. You'd also mentioned Hercules, which is a large, huge remotely operated vehicle that you have. But can you tell us a little bit about the difference between the Argus and the lower ROV?
Sure. So the technology we use to explore, Argus and Hercules, are a two-bodied system. So Argus is a tow sled. So that basically is keeping an eye on the ROV as it's working under the lights of Argus and the cameras of Argus. So Hercules is an example of an ROV that is more or less neutrally buoyant. It can fly around like a helicopter on the seafloor, driven by a pilot who's using a control stick to maneuver it. Argus is connected to the ship via cable that you move when you move the ship. So as the ship moves, Argus can move, and it's on a winch, so we can regulate the distance or the altitude of Argus above Hercules in those cases. Yeah.
Very amazing. I've seen them both in action up close and personal. But you are the director of the Inner Space Center.
Right.
So technology like crazy at the Inner Space Center. So can you tell us a little bit about the underwater realms that the Inner Space Center beams live to people? Why? I mean, why is it important to beam it live?
Well, so the Inner Space Center is connected very closely to two ships of exploration: the Oceanis-Explorer, which is a NOAA ship, and the EV Nautilus, which is Dr. Robert Ballard's ship of exploration. And so they are out working in the world's oceans, exploring the seafloor. And because when we run an exploration program, it's very difficult to staff the right expertise on the ships for making discoveries or knowing what you're looking at really at all times. So we take advantage of telepresence technology to do that. And so the telepresence technology basically is the same way we're connecting to the Morgan right now. It's using advanced technology. In the case of the Nautilus and the Oceanis-Explorer, they use a satellite link to stream video and manage audio and data feeds to and from the ships. What we're doing with the Morgan is a microwave system, so a little bit different technology. But it's very important to have the telepresence technology, because then we can network in people from all over the world and to watch the feeds in real time, kind of like what we're doing with the Morgan. And then we can network in those experts to help us understand what it is we're looking for on the seafloor. So it's very, very important.
Very cool. So you mentioned buoys and other things earlier. Real quick before we go to Ivar, to tell us a little bit about the different connections between the Rowan and the Morgan and here at the monument, how that worked, and then of course a little bit into more detail about some more technology. I know we have our other 38th Voyager standing by with Matt out there. But it looks like our audio might be down, so this great technology we're talking about isn't working so hot. But we're good.
Kate,
Matt, are you there?
I'm here, Kate. Can you hear me okay?
Yeah, okay, great. So we were just talking about drifter buoys and technology and how that works. So I think you have somebody queued up here, Frank Reed, or I'm sorry, Mike Witney, who can tell us a little bit more about the buoys that he's been putting out during the voyage.
Fantastic. Yeah, that's right. Standing right next to me here is Mike Witney, who, as a 38th Voyager, has got a very special project involving drifters. Mike, you want to give us a little sense for your drifter project?
Well, yes, we are able to release 5 drifters today, and they're surface ocean drifters that track the movement of the water, and they'll report back their position to the internet every 2 hours. We hope for weeks and maybe even months. It'd be wonderful to get throughout the summer and into the fall. And with that, we'll see the connections between the waters that flow over Stelwagen Bank and then the rest of the ocean waters, where they go to over time and how those paths change.
So these drifters, when I saw you putting them over the side, they looked kind of low-tech. Tell me how you make these.
Well, they're purposely low-tech because they're built from everyone, from me to grad students, undergrads, and even kindergartners, first graders, second graders, and my daughters designed the artwork. So it's a home-built drifter with a high-tech GPS on top of it.
And so really it's important to release a number of these things rather than spend a lot of money on one of them. Is that true?
That's it. If the lower the cost is per drifter, the more we can release and the more we can learn about the different pathways that water takes. And this is after a project, a real program that NOAA's done, headed by Jim Manning at the Northeast Fisheries Science Center. And it's wonderful. They've released hundreds of drifters over the year and really raised awareness for how you can do science in the ocean and ocean flows and how we're connected to different parts of the ocean.
So ocean currents and ocean circulation are tremendously important for just the health of the Earth. Can you give us like a sense for really what that means?
Well, most of my research tracks river water, and so we start in the rivers and track out into an estuary and then even out into the open ocean. And some of what we do tracks it globally, like the globally significant rivers, Amazons, out far into the ocean, and the effects it has on not just where the water itself goes, but where nutrients, where sediments, and where pollutants and contaminants go too.
Certainly the pollution and contamination is something that's very important to keep track of. I could understand that.
Right, and we know that we are putting pollution into the near waters, but I think we've got to appreciate that gets out into the open oceans, some of the areas we think of as pristine. We need to protect them by keeping our waters close to shore clean too.
And it would seem the best way to do that is to start at home and close to shore in those lakes lakes and rivers that are right in our backyard.
I think so. Pay attention to what you put in the waters, and if there's something that you see that shouldn't be in the water, should call the appropriate authorities.
Mike, thanks so much for stopping by here to tell us all about your drifter program. I hope we'll be able to release more drifters.
Me too. Thanks very much, Matt.
Kate.
Thanks, Matt. And Mike, thanks so much for telling us about the drifters. And we're going to stay with the University of Connecticut and go here in studio to Ivar to tell us a little bit more about these different technologies. And Dwight was telling us a little about remotely operated vehicles. But let's go through the span of technology. You've got a great graphic where you explain the difference between scuba diving all the way up to autonomous underwater vehicles.
Well, the ocean is really, really complex, both in space and in time. And really to understand the ocean, we need to understand both of those dimensions. So all the way down, as you say, from being able to look at something in a fine scale, like using a remotely operated vehicle or even a diver, or now we're getting even smaller scales with genetics to understand the makeup of these organisms, all the way out to using the multi-beam sonars that we were talking about to give us that satellite view of the sea floor. So that gives us this landscape view that we can understand the different habitats of the sea floor. And then on the time scale, we have buoys that sit out there, or drifters that are out on the water for days, weeks, months at a time. So we understand all of these dynamics that occur in the ocean over time, driven by storms, driven by the natural currents and so forth. So it takes this combination of technologies to understand the ocean. So.
Well, you looked at this great ocean technology framework that you had put together from diving all the way up to satellites and how we use them. There's also this place called Aquarius that's actually located in the Florida Keys National Marine Sanctuary. Talk about amazing technology for people to be able to live under the ocean I lived under the ocean for 10 days at a time in Aquarius, and I think Fabienne Cousteau just broke a record, 31 days under the ocean in Aquarius habitat. Can you tell us a little bit about that habitat and how it enables us to do good research under the ocean that you might not be able to diving or using AUVs?
Well, again, what the Aquarius allows us to do is to combine the human element, to have a human researcher down there with their intelligence, their eyes, their hands, working in fine scale in a coral reef ecosystem, such as down in the Florida Keys National Marine Sanctuaries. But they have the ability to stay down there for a long time. So they can put out experiments. They can go back out and revisit those experiments. So they have a combination of the human element and allowing that human to stay active and studying, in that one spot over a longer period of time. So it provides a great combination of time and humanity to study.
So Dwight, the 38th voyage is pretty impressive. You live up here in New England as well. So right there in Connecticut, right near the Mystic Seaport. So why is it so important to continue the tradition of ocean exploration? And how can the Charles W. Morgan mission help us to appreciate that tradition and better understand the world we live in.
Right. Well, just earlier today we saw whales that were breaching right here, and I think the Morgan right now is only 7 or 8 miles or so offshore. And so, I think it's very important to bring recognition to the fact that these resources are right there, right near our shorelines, and we sort of forget that because we're land dwellers, and we don't really venture too far out into the oceans. There's a few of us that do, but the oceans are vast, they're unexplored. We know very little about the details of the oceans, how they influence climate change, how they sort of regulate the heat budget of the Earth, how they adapt to change itself, whether it's pollution or warming or ocean acidification, you name it. All these are worthy of study more so that we can understand more about the ocean. So that really begins with fundamental exploration. If we need to understand the marine environment, we need to go there, we need to look, we need to collect some samples, collect some data, process that information, and then you can start saying things that are intelligent about how the oceans evolve or what might be forecast for the future for the ocean. So it all begins with exploration. So we're doing our little part, but it's important that the public knows about what we do, and the Morgan's a great example of a ship that the public can go visit at Mystic Seaport and gain an appreciation for how explorers worked hundreds of years ago, and how that has changed over time and to what we do in modern days.
Well, thanks, gentlemen. We're going to wrap up our interviews and go back out to Matthew Lawrence on the deck of the Morgan and one of the world's most accomplished ocean explorers, Dr. Sylvia Earle. Matt?
Hi there, Kate here. Well, we are just north of Cape Cod off of Race Point, and the sail is starting to wrap up today here. We've just taken the tug back on our port side, and we're going to be rounding Race Point to head into Provincetown Harbor. But before that happens, I hope we can have a moment to speak with Dr. Sylvia Earle and get her take on the 38th voyage. Sylvia, do you have an opportunity to chat with us for a second?
Indeed.
Very nice.
Just signing a copy of The World is Blue for the ship as a commemoration of the 38th voyage.
That's fantastic. Fantastic. Nice of you to sign that for the ship. I'm sure everyone will appreciate it.
Well,
we're here talking about technology, and you've had a lifetime of experiencing technology. You've dived with rebreathers, lived in underwater habitats, used submersibles.
30 different kinds.
So where do you see ocean technology going in the future?
Onward and downward, of course. We need to do as much for the ocean and this part of the universe as we have in exploring the universe above. We've invested in aviation and aerospace. It's paying off handsomely. We've neglected the ocean, and it's costing us dearly. But now we know, or at least we have an idea of the magnitude of our ignorance and the hunger, the need to really understand how better to take care of the natural systems that keep us alive. We didn't think it was possible for humans to alter the nature of the ocean, let alone the nature of nature as a whole, when I was a kid. One of the great discoveries of the 20th century and now into the 21st is realizing the immense power that we have to undermine the world that keeps us alive. And a part of what has given us this insight is looking up in the sky, looking at that turning of technology to explore the heavens and realize in all of the universe or any other universe that we might dream of out there, this is really a special place. And it's right here. I love the idea of going to the moon, Mars, Jupiter, and we should do this, but with a sense of urgency as never before. We need to study this planet, this part of the universe, and do everything we can to take care of it and to hold the planet steady. We know how to rock it. We have rocked the underpinnings of our life support system here on Earth. What we've done to the atmosphere, what we've done to the waters of the world, what we've done to wildlife that isn't just there for us to consume for fur or for meat or whatever we want to use the various creatures that share the planet with us for, but it's that we're all in this together, that all creatures on Earth, including ourselves, shape the way the world works. And we've been the beneficiaries of hundreds of millions, even billions of years of preceding fine-tuning. We have a planet that works in our favor. Let's keep it that way. Let's do everything we can to restore the damage that we've done.
So some of this technology here, these improvements that we're seeing and better be able to understand the planet, are they going to be all a force for good? Is this technology helping us move forward with your vision?
Well, technology, like fire, like anything, it's what we do with it. It's not in itself intrinsically good or bad, but we have the capacity to use the technologies that have been developed in recent centuries, especially recent decades, and mostly in recent years, even recent months. The pace is picking up about our capacity to shape the world in our favor or not. And I think the key to it is exactly what you're doing now. It's in communication. Once people know, they can care. They can't care if they don't know. It's really simple. And throughout most of history, we haven't known of why the natural systems matter. We've thought maybe they're beautiful, or that they're a place for recreation, or a place to take things, whatever the natural world has been used for. But considering the ocean, and here we are on the Charles W. Morgan, its destiny when it started out as a young ship was to go out and kill. It's a killing ship. It was a taking ship. Let's find the whales, kill the whales, treat them as products. Big part of the economy of the part of the world where the Charles W. Morgan is now home based. It was built on the bodies of dead whales and dead fish and dead wildlife generally, birds too. But now we understand their other values. And it's not just here in this part of the world, it's around the world that you know that a dead elephant has value, but nothing like a live elephant. A dead shark has value, but nothing like the value of a live shark or a live tuna, a live cod. And it's this critical transition time that we're in right now, seeing those other values. It gives a cause for hope. This vessel, this Charles W. Morgan, is a ship of hope because we're coming from the past into a new future. We're armed with knowledge and people who care. It's really a wonderful moment to be around.
Well, I certainly feel the same way. And we had some really spectacular sightings of whales today. I understand that you maybe speak a little whale?
Ooh, 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 oh, oh.
That sure sounds like it to me. Well, Kate,
Thanks,
coming
Matt.
to you live here from the deck of the Charles W. Morgan.
Thanks,
Here we
Matt.
are.
That's awesome, and thank you, Sylvia. You speak some excellent whale. I'm wondering if it's humpback, minke, fin, sperm. I don't know which sound that was. I guess sperms are clicks. But anyway, thanks, Matt, and we will check back in with you tomorrow morning as the Morgan kicks off another day of sailing from Provincetown to Stelwagen Bank. I want to thank all my guests, both here in the studio and on board the Morgan, for joining us throughout our first day of streaming coverage. And of course, thank you specifically to you gentlemen to make this link happen, for sure.
You're welcome.
Pleasure.
It's very exciting.
So that does it for our broadcasts today, but there's plenty more Oceans Live coverage to come this weekend. Tune in tomorrow and Sunday at 10 a.m., noon, and 2 p.m. Eastern. Thank you to the Mystic Seaport and to our hosts here at the Pilgrim Monument and Provincetown Museum, and to all our partners who have helped make this entire show possible. This has been Kate Thompson for Oceans Live. Thanks for watching, and we'll see you tomorrow right here on www.oceanslive.org.
Rough, tough life of toil and strife we whalemen undergo. We don't give a damn when the gale is done, how hard the wind does blow. We're homeward bound, it's a damn fine sound, with a good ship taut and free. We don't give a damn when we drink our rum with the girls of Old Maui. Rolling down to Old Maui, me boys, rolling down to Old Maui. Yeah! We're homeward bound from the Arctic ground, rolling down to old Maui. Once more we sail with a northerly gale through the ice and sleet and rain. Them coconut fronds on them island lands we hope to see again. 6 hellish months have passed away on the cold Kamchatka Sea. But now we're bound from the Arctic ground, rolling down to old Maui.